For years, diffusion was the recipe behind almost every image generator. But there's a newer, cleaner idea that's quietly taking over, and it already powers models like Stable Diffusion 3 and a whole wave of video generators. It's called flow matching, from a paper by Lipman and colleagues in 2022. Now, it's closely related to diffusion, but the way it's framed is simpler and, in many ways, a lot more elegant. Let's unpack what it actually learns, why the training is so cheap, and why that makes generation so fast. The easiest way in is to contrast it with the diffusion recipe most people already know. Diffusion frames generation as a noising, then denoising chain. You gradually corrupt data into noise, then train a network to reverse that, walking backward along a curved, stochastic path. It works beautifully, but the path is wiggly and full of randomness, and following it faithfully tends to take a lot of small, careful steps. Flow matching reframes the whole thing. Instead of a denoiser, it learns a velocity field, a vector at every point in space and time that says which way and how fast a sample should move to travel from noise toward data. Think of it as a current in a river that carries every drop toward the sea. And the most common recipe uses nearly straight paths between the two, which is exactly why it can generate so quickly. Let's walk through the actual setup, because seeing how a sample is built makes the velocity idea concrete. Everything begins with a pair. You draw a random noise point and a real data point. These are the two endpoints, the place you start from and the place you want to end up. Between those 2 points, you define a path, and the popular choice is a straight line, an approach often called rectified or linear flow. At any moment along that line, there's a clear target velocity, simply the direction pointing from noise straight toward the data. Now you train. The model looks at a point sampled along that path and tries to predict the target velocity there. It's plain regression, matching predicted vectors to target vectors, and crucially, it never has to run the full trajectory during training. You just probe random points and correct the model. That property is what people mean by simulation-free, and it's a big reason the method is so much cheaper to train. At generation time, you start from pure noise and follow the learned velocity field forward, integrating it step by step until you land on data. Because the paths are close to straight, there's very little curve to chase, so only a handful of steps gets you all the way there. Boil it all down, and 3 ideas really define flow matching, and each one buys you something concrete. It learns a velocity field, not a denoiser. The model's job is to output the direction of motion at every point, describing a smooth flow that carries noise into data. Training is simulation-free along nearly straight paths. You match velocities at random points without ever unrolling the full trajectory, which makes the objective simple and the training cheap. Generation is fast because the paths are close to straight. A nearly straight route needs very few integration steps, so sampling can be dramatically quicker than classic curve diffusion. All right, let's lock in the essentials. Flow matching is a simpler alternative to diffusion from Lipman and colleagues in 2022, now behind newer image and video models. Rather than denoising, it learns a velocity field that transports noise toward data along nearly straight paths. Training just regresses onto target velocities at random points, so it's simulation-free and cheap to run. Because the paths stay nearly straight, generation needs only a few steps. If you enjoy watching these ideas demystified, we do it every week over at standardy.com. Hope to see you there.